Picture this, a handful of processes, each holding on to something the others need, and not one of them willing to let go. The whole system just freezes. That's a deadlock. And over the next few slides, we're going to unpack exactly how it happens, and more importantly, how the operating system breaks the stalemate. We'll cover the 4 classic conditions, the single cycle that defines a deadlock, 2 main recovery paths, and a few core concepts to tie it all together. So here's the roadmap for our journey. We'll start with a simple definition of what a deadlock actually is, then look at the 4 conditions that must all hold true for one to occur. From there, we'll explore the strategies an operating system can use to handle them, how to detect deadlocks once they've taken hold, and the recovery techniques that break them apart. We'll close with the trade-offs, because no single approach wins in every situation. Let's start with the basics. A deadlock happens when 2 or more processes get stuck waiting on each other indefinitely, each one holding a resource the other needs and neither willing to let go. Picture 2 cars meeting on a 1-lane bridge. One occupies the left half, the other the right, and both just sit there expecting the other to reverse. Nobody moves, nobody yields, and without outside intervention, they'll wait forever. That's a deadlock in a nutshell. Let's make that concrete with the simplest possible setup. Process P1 is holding resource A and needs resource B to continue. Meanwhile, P2 is holding resource B and needs resource A. Each one is sitting on exactly what the other is waiting for, so neither can move forward. There's no bug in the logic, no crash, no error, just 2 processes politely waiting on each other. Forever. That's the essence of a deadlock. Now, that little standoff isn't an accident. It only happens when 4 very specific conditions all line up at once. These are known as the Coffman conditions. First, mutual exclusion. A resource can only be held by one process at a time. Second, hold and wait. A process clings to what it has while reaching for something more. Third, no preemption. Nobody can rip a resource away. It has to be given up voluntarily. And fourth, circular wait, a closed loop of processes, each waiting on the next. Remove any one of these and a deadlock simply cannot form. That 4th condition, the circular wait, is actually something we can see visually using a resource allocation graph. Circles are processes, squares are resources. A solid green arrow means a resource is assigned to a process, and a dashed cyan arrow means a process is requesting one. Here, P1 holds A but wants B, while P2 holds B but wants A. Trace the arrows and you'll walk a closed loop right back to where you started, and that loop, with single instance resources, is your deadlock staring back at you. So, once we know a deadlock can form, the natural question is, what does the operating system actually do about it? Broadly, there are 4 strategies. Prevention means designing the system so one of those 4 conditions can never hold in the first place. Avoidance is more dynamic. We grant resource requests only when we can prove the system stays in a safe state. And the classic example here is Banker's algorithm. Detection and recovery takes the opposite stance. Let deadlocks happen, but watch for them and break the cycle when they appear. And finally, there's the ostrich approach. Just ignore it and hope it's rare enough not to matter. Believe it or not, that last one is what most general-purpose systems actually do. Now let's zoom in on that 3rd strategy, detection and recovery, because that's where the rest of this deck lives. Think of it as a 3-step pipeline. First, the OS detects that a deadlock exists, then it decides how to break the cycle, and finally, it recovers by actually freeing up resources so work can resume. The first 2 steps we'll touch on briefly, but our real focus is that last step. What actually happens once the system has confirmed? Yes, we're stuck. So how does the OS even know a deadlock has happened? There are 3 common approaches. The cleanest is a wait for graph, where the system tracks which process is waiting on which resource. If those arrows form a cycle, you've got a deadlock. Alternatively, the OS can run periodic checks on a timer, or simply use timeouts, assuming that any process waiting too long is probably stuck. The trade-off is really about frequency. Check often and you catch deadlocks fast but pay in overhead. Check rarely and it's cheap, but processes sit frozen longer. Once detection confirms a deadlock, the OS has to actually break it. And there are really two broad strategies on the table. Option A is process termination. Pick a victim, kill it, and reclaim everything it was holding. Option B is gentler. Resource preemption, where instead of killing the process, you just yank a specific resource away and hand it to someone who needs it. Both work, but as you'd guess, they come with very different costs. Let's zoom in on path A, process termination. The blunt approach is to abort every deadlocked process at once. It's simple and it absolutely breaks the cycle in one shot, but you throw away a mountain of completed work and force a lot of restarts. The gentler version kills them one at a time, rechecking after each, which preserves more progress and is less disruptive, at the cost of running detection again after every kill, so resolution takes longer. So if we're killing them one at a time, how do we pick the unlucky one? The OS weighs a few things. Priority comes first. Low priority work goes before anything critical. Then progress. If a process is nearly done, killing it wastes all that effort. Resources held matters too, because terminating a process, hoarding many resources, frees up the most at once. And finally, restart cost. How painful is it to run this thing again later? Balance those four and you've got your victim. But killing isn't the only option. There's a gentler path. Instead of terminating a process, we just borrow a resource from it and hand it to someone else, breaking the cycle without losing the work. 3 things to get right here. Pick which resource to take in a way that minimizes cost. Roll the victim back to a safe earlier state so it can resume cleanly, and rotate your choice so the same process isn't always the one losing out. The catch? Some resources just can't be cleanly taken back. A printer halfway through a job, or a file mid-write, you can't simply pause and hand those off. And that rollback we just mentioned, it only works if we've been saving state along the way. The OS periodically takes a checkpoint, a snapshot of where a process was, so it has somewhere safe to return to. With that in hand, we can do a partial rollback, undoing just enough to free the resource we need, or if no checkpoint exists, fall back to a total rollback and start the process over. There's a trade-off, of course. Checkpoints cost a little overhead while everything's running smoothly, but they pay for themselves the moment a deadlock actually hits. But rollback raises a new worry. What if the OS keeps picking on the same unlucky process every time? It gets killed, restarted, killed again, and never actually finishes. That's starvation, and it's just as harmful as the deadlock we were trying to solve. The fix is fairness. Track how often each process has been chosen as a victim, factor that count into the cost so frequent victims drop down the list, and set a hard upper bound so no process can be preempted more than n times. The guarantee we're after is simple. Every process must eventually make progress. With both strategies on the table, it's worth putting them side by side. Termination is fast and simple. You kill the process, resources come back instantly, but you throw away all of its work, so it fits cheap, restartable jobs best. Preemption is slower and more complex because you have to roll state back carefully, but you save more of the work, which makes it the better choice for long-running processes you really don't want to lose. So how do real systems actually handle all this in practice? It turns out the approach really depends on the stakes. General-purpose operating systems like Linux and Windows mostly just ignore the problem. It's called the ostrich algorithm because deadlocks are rare enough that a reboot is an acceptable fix. Databases like PostgreSQL and MySQL take it more seriously. They actively detect deadlocks and abort one transaction, the victim, to break the cycle. And in real-time or safety-critical systems, deadlock simply isn't allowed to happen. They're designed from the ground up to prevent it entirely. So, which strategy fits your situation? Ask a few honest questions. If deadlocks are vanishingly rare, just ignore them. A reboot is cheaper than the engineering. If you need guaranteed uptime, pay the cost up front and prevent or avoid them entirely. If resource usage is unpredictable, lean on detection and recover after the fact. And when processes are long and expensive to redo, prefer preemption with checkpoints over outright killing them. Let's pull it all together. A deadlock is what happens when processes get stuck in a cycle, each waiting on something the other holds. Nobody moves, ever. It only happens when all four conditions line up: mutual exclusion, hold and wait, no preemption, and circular wait. When it does strike, you've got two recovery levers: kill the offending processes or preempt their resources and roll back. And whichever path you choose, keep an eye on starvation. Rotate your victims, or some unlucky process will pay the price forever. So that's the whole story in 2 lines. Detect the cycle, then break it cleanly. Recovery isn't about avoiding pain entirely. It's about getting a stuck system moving again with the smallest possible cost in lost work and fairness. If you want to go deeper into operating systems, Linux, and DevOps, head over to dargslan.com for courses, cheat sheets, and CLI tools. And if this helped, subscribe, like, share. See you in the next one.